Every story has a beginning, even the story of the universe. Some 13.7 billion years ago, a mysterious event thrust the universe into motion in a big bang. The ultimate creation of every atom, every star, and every galaxy. But this is our story. How for thousands of years we've pieced together a vision of the universe, made sense of it through science, and discovered our place within it. This is our story of everything, from shaman to scientist, beyond the Big Bang. For thousands of years, we've gathered our observations of the heavens into books that would more than fill a library. We've built a vast body of knowledge about our universe. How it all began, how it will end. It's a work in progress. The script is still being written. The ink is still wet on the page. Where do we begin? Let's begin at the beginning. Let's begin with the Big Bang.
The Big Bang is a theory of cosmic evolution. It tells us how the universe evolved, how it changed from a split second after whatever brought it into existence, and we still don't know what that is until today.
When you look out at the universe and look at the other distant galaxies, you see that they're all fleeing away from us, that they're all moving outward at huge velocities. If you extrapolate that all the way back, you see that one time, maybe 13 or 14 billion years ago, everything that there was must have been compressed into one inconceivably dense point.
We know we don't have the whole story, but we've never had the whole story in the history of physics. We've had a series of better and better approximations revealing startlingly more and more beautiful and interesting truths.
The Big Bang is our theory for the beginning of the universe. But for a long time, people either didn't think about the origin of the universe, or they assumed the universe had always existed and was everlasting. Even scientists were reluctant at first to embrace the Big Bang.
It was meant to be a derisive term. However, the Big Bang is really a contradiction because it was not big and there was no bang. It wasn't big because we think that the universe started from a singularity of some sort, and there was no bang because there was no air to carry the vibrations. So a Big Bang is in some sense is a misnomer, but the name stuck.
And so has the theory.
Right now I would say that the Big Bang theory is a solid part of science as we understand it. Anybody who doesn't accept it is regarded by most of the people in the community as essentially a crackpot.
But acceptance and understanding are two different things. The Big Bang theory doesn't yet provide all the answers science seeks to explain how our universe was born.
What cosmologists are referring to when they talk about the Big Bang theory is really only a description of the aftermath of the bang. The conventional Big Bang theory says nothing about what banged, why it banged, or what happened before it banged.
Right now, at this very second, we're in the aftermath of the Big Bang. Everything we see and hear and taste and smell and touch is the aftermath. The Big Bang is really our evolving, expanding universe. For us, mostly stuck on our rocky little planet, the view of the universe begins with Earth. This is Earth, silicon and oxygen-based, with a metallic core. The surface is mostly water. It teems with life and rotates once every 24 hours while orbiting a star called the Sun every 365 days. This is the Sun, mostly hydrogen and helium. Its surface temperature is nearly 10,000 degrees Fahrenheit. For energy, our Sun converts 700 million tons of hydrogen into 695 million tons of helium every second. The Sun is part of a solar system formed around 4.5 billion years ago that includes Earth and 7 other orbiting planets from Mercury to Neptune. And it isn't a stationary system. Our solar system is spinning, flying through space at 134 miles per second, turning in circles as part of a vast collection of stars and star systems. There may be 200 billion stars in this collection called the Milky Way galaxy. An estimated 6 billion of those stars with planetary systems like ours. Our solar system orbits the center of the Milky Way on one of its outer arms. The Milky Way is one of more than 125 billion galaxies that make up the visible universe. This is the universe. It's really, really big. And it's getting bigger. It's expanding. If the universe is expanding, then it used to be smaller. Much smaller. In fact, if we went back in time, we could watch it shrink. Back far enough, and the universe would be smaller than a galaxy. Back, and the universe is smaller than our solar system. Farther back, and everything that exists fits inside a stadium, a coffee cup, an atom. 13.7 billion years ago, the universe was smaller than the smallest part of an atom. Unbelievably small. Then, something happened. In a flash, everything suddenly expanded. This was how it all began. The first moment of existence. What we now call the Big Bang.
And that's what we know to be true, not because theorists have invented it, but because all the observations tell us. We can predict the abundance of light elements, and they agree over 10 orders of magnitude with what we see. So that fundamental picture that the universe is expanding and emerged out of a hot, dense universe, the finite time in the past, is the Big Bang picture.
The theory of the Big Bang isn't the sort of thing you figure out overnight. It takes years, centuries of collected wisdom. Mankind has been thinking about this for a long time. Even before we realized it, we were thinking about it. Every time we looked up at the stars, we were thinking about it. How do we know what we now know? How did we figure it all out? That's the heart of our story. The story of how our concept of the universe evolved.
We stockpile the discoveries of the most brilliant members of our species, allowing us, however strained and with whatever struggle it involves, to slowly ascend the ladder of knowledge. Maybe compensating for the fact that any one of us is just too stupid to figure it all out.
So, where do we begin? Today, Professional astronomers and physicists on campuses like the Massachusetts Institute of Technology and Cambridge University in England waged debate about the Big Bang Theory. But the conversation began a long time ago, before anyone ever heard of the Big Bang, before anyone knew what the heavens really were.
Way before science existed or was even a contemplation in the minds of anybody, people were asking questions about origin.
When early man looked at the sky, he saw it dominated by the warming, life-giving sun. At night, he saw the moon and stars. This was the universe, harsh, hostile, and chaotic, with a drifting sun that shifted across the sky as the seasons went from warm to cold. Primitive people needed to understand their world in order to survive it.
People had absolutely no control over nature. The balance of the expected and the unexpected made people make nature into gods in order to establish some kind of relationship with them.
Without telescopes or modern observatories, primitive people relied on simple structures to help them understand the skies. At places like Stonehenge in England or Chichen Itza in Mexico, they attempted to connect with the heavens, the perceived home of the gods. These were simple instruments of observation and tools of analysis that helped make sense of the dancing universe.
We are here in the eastern part of Germany, some 100 kilometers south of Berlin, in a little village called Goseck. One of the oldest monuments concerning sun, moon, and stars was found here. This is the solar observatory at Goseck. It was built 7,000 years ago and was used by the early farmers to tell the time in the year.
Constructed 2,000 years before Stonehenge and reconstructed here, this is Europe's oldest known calendar. During the winter and summer solstices, the shortest and longest days of the year, the setting sun lines up with gates in the Palisades. Knowing these dates helped these people understand the life-giving sun.
The night sky is a clock. It is a gigantic clock staring you in the face, and it allowed the ancients to calculate when to plant, when to harvest. In other words, their very livelihood depended upon their understanding the motion of the sun and the heavens.
This idea of astronomy predicting the behavior of the natural world based on the motion of the heavens gets mixed up with the dogma of astrology, the belief that the motion of the heavens predetermines our fate, that a meteor signals military victory, a new star, the birth of a king.
Back then, astronomy was predicting the motion of the stars. Astrology was predicting how those stars affected us. And it's really hard in the ancient mind to separate those two. That if you understand the clockwork of the heavens, you understand how our fate is going to be.
Astrologers divided the sky into regions as early as the 6th century BC. They saw shapes in the stars and named the regions after these shapes: Aries, Taurus, and Gemini, among others. But as astrologers gazed at starry skies to divine their fate, they also watched and learned how the heavens moved. From superstitious motives came the baby steps of scientific observation.
I see science as a journey that our species has been on for roughly 2,500 years to try to come to grips in as deep a way as possible with the universe, the laws of the universe, the structure of the universe. What makes things up? How do they evolve? And what are the forces that govern change?
But sometimes, simple observations can lead to fundamentally wrong conclusions.
When we look out at the universe, the first sense you get is that we're the center of the universe, that the universe is revolving around us. Stars go across the night sky, the sun goes across during the day, and the sense was that the earth was fixed and that the heavens rotated about us.
But that perception is completely wrong. Earth isn't fixed. It's not the center of anything. The whole history of cosmology is the relentless retreat of Earth from center stage. Nevertheless, the gathering of knowledge moved forward. Using mathematics, the ancient Greeks provided more detailed information about our dominant celestial neighbors, the sun and moon.
Even back then, 2,000 years ago, they knew that the Earth curves. And by looking at the shadows, they calculated the size of the Earth to within about 10% accuracy. They actually calculated the distance from the Earth to the moon and the rough dimensions of the distance from the Earth to the sun. So in other words, the ancients were no fools.
The ancient Greeks also recognized two types of stars. Most were fixed and small and moved together. A few were larger and moved haphazardly, or so it seemed. These were planets, and predicting their motion became a centuries-long goal. With just their naked eyes to scan the skies, the Greeks saw only 5 planets, naming each after their gods. Today, we're more familiar with their Roman designations: Mercury, Venus, Mars, Saturn, Jupiter. Ancient astronomy assumed a concept of the universe proposed by 4th century BC Greek philosopher Aristotle, who imagined the Earth at the center of the universe, with the sun, moon, stars, and planets all revolving elegantly around it in perfect crystalline spheres.
Aristotle's universe was finite. It was a big sphere. Actually, it was like onion. It was an onion with many concentric spheres.
1st century astronomer Ptolemy improved on Aristotle by accurately tracing the paths of the planets, which didn't move haphazardly after all. Using complex circular motions called epicycles, Ptolemy could predict their prescribed paths and changing velocities. In other words, Ptolemy's system reliably predicted the future behavior of the planets, another step in man's journey to understand and control the universe.
The Ptolemaic system was extremely complex. It had all these planets going in loops, and it worked beautifully, but it was just wrong. The idea that you can predict something doesn't mean you understand the fundamental principles behind it.
Ptolemy's system did not accurately reveal the universe, but it didn't try.
He essentially showed that the positions of the planets could be calculated for any time past or future. It was a tour de force of mathematical understanding. Interestingly, the astronomy seemed to stand still for centuries after that.
In fact, after the collapse of Rome in 476 AD, astronomy actually lost ground.
Europe fragmented into smaller powers, and a lot of the wisdom of the Greeks was lost.
1,000 years later, a new theory would confront accepted beliefs about how the heavens worked and would move mankind one step closer to a theory of the Big Bang. During the 15th century AD, An idea called heliocentrism claimed the sun, not the Earth, was at the center of the universe. This horrified Christian clergy, who felt it contradicted the Word of God. If God created Earth and man in his own image, then Earth and its devout inhabitants must be the center of everything. Ironically, the champion of a sun-centered universe was a devout church deacon from Frombork, Poland, named Nicholas Copernicus.
He was a cathedral administrator, working to help collect the rents, helping people who were sick. But in between, he was working on astronomy.
Copernicus was troubled by Ptolemy's complex heavenly mechanics. But he found an elegant solution. When he moved the Earth from the center of the solar system and replaced it with the sun at the heart of it all.
When Copernicus put the planets going around the sun, he discovered that the planet Mercury, which goes around in about 3 months, automatically fell closest to the sun. And Saturn, the slowest planet, which goes around in about 30 years, automatically fell at the outside edge. Copernicus wrote, "In no other way do we find such a sure harmonious connection between the size of the orbit and its period." That seemed almost magical.
Copernicus also insisted that the Earth was rotating, that it spun completely around on an axis every 24 hours. The heavens didn't move. We did. Stars chasing across the sky each night were merely an illusion created by the rotating Earth. Likely afraid of church reprisals, Copernicus withheld publishing his theory until he was on his deathbed in 1543. But his book, Concerning the Revolutions of the Celestial Orbs, paved the way for Johannes Kepler, born in 1571, the champion of observational science.
Kepler was the real hero here because he was the one that really came out and trumpeted to the world that the sun has to be the center.
Kepler had at his disposal a trove of astronomical data collected through years of staring at the sky.
When he chugged through his observations and did the calculations, realized that not only was the sun center of the solar system, but the perfect circles were a figment also. It was uglier philosophically, but it really matched the data.
Kepler improved on the Copernican system by hypothesizing that the planets traveled not in perfect circles, but in ellipses around the sun. Kepler's data also pointed to a strange phenomenon he struggled but failed to understand. As planets approach the sun, they speed up. Further away, they slow down. Together, the sun-centered universe and the variable speed of the planets best explain what we see here on Earth.
Suddenly, and for the first time, the sun-centered picture gives better predictions than the Earth-centered picture. And then you have not only something that's driven by data, but does what science is supposed to do, which is to make predictions which are good.
But as one cosmic riddle appeared solved, another remained. Kepler saw that the sun influenced the speed of the planets as they traveled through space. But how? Before anyone addressed this mystery, dogma and science collided in a conflict that reverberates to this very day. At the turn of the 17th century, Italian astronomer Galileo Galilei would take the theories of Copernicus and Kepler, that the sun was at the center of the solar system, and prove them right beyond any shadow of a doubt. He did this with a new technology that would change the course of history.
The telescope, in some sense, is the most blasphemous, the most seditious, the most revolutionary, and the most splendorous instrument of science.
All of science received the greatest of gifts in this tool that brought distant objects close.
Once the idea got out that you could take two lenses, line them up in such a way, put them in a tube, and make a spyglass out of it, that would spread like wildfire around the world, as it did. And so the issue now is not who's got the telescope, but do you now know what to do with it? Are you looking in people's windows, or are you looking up and out into the universe?
Galileo improved on the design in 1609 by grinding his own lenses and creating one that could magnify an unprecedented 30 times.
And with that telescope, for some reason, he decided to look at the sky as opposed to the incoming ships to the Republic of Venice. And what he saw completely changed the scope of astronomy.
Galileo was treated to the clearest, most detailed view of the heavens any person had ever known. Through his telescope, Galileo saw thousands more stars. A moon pocked with craters, satellites circling Jupiter, Saturn with giant ears. Greatest of all, Galileo plainly saw that Venus went through phases like our moon. Clear evidence that Venus orbits the sun. Proof of a sun-centered solar system.
It showed for the first time that Copernicus was really right. The Earth wasn't the center of the solar system, the sun was. So Galileo, with his telescope, pushed the Earth away from the center of the universe and said, we're not the center of everything. We're one planet among others, and there could be a much larger universe than we know.
What Copernicus had assumed for aesthetic reasons, what Kepler deduced through measurements and mathematics, Galileo proved. Galileo saw. Galileo revealed.
The ancients had seen everything that could be possibly seen to the naked eye. It really took a new instrument to get beyond that. The telescope, that was where the breaking point was between the ancients and the moderns.
Centuries of church dogma claiming Earth was the center of the universe was now plainly wrong. With the Catholic Church still reeling from the schism of the Protestant Reformation, Galileo's discovery appeared to undermine Scripture. Dangerous for a church that felt under siege. Dangerous for a scientist proposing it. Nevertheless, Galileo, a devout Catholic, published his observations in a book called The Starry Messenger in 1610. Surprisingly, the Church welcomed Galileo's findings at first.
Had Galileo been a little more careful in his approach, he might have gotten away with it. One famous quotation from Cardinal Baronius, a predecessor, was, "The Bible tells us how to go to heaven, not how the heavens go."
Ultimately, Galileo's downfall was not his inability to sway the Church to his way of thinking. but rather his attempt at interpreting Scripture all by himself, independent of the Church.
Galileo quotes the famous St. Augustine, who said that if you found an interpretation of Scripture which seemed to be contradicted by well-established knowledge, then you should reconsider that interpretation of Scripture.
But the Church, concerned with perceived threats to its own power, could not concede biblical interpretation to Galileo. In 1633, after Galileo published a new book championing the sun-centered system, the Pope summoned him to stand trial for heresy.
He's forced to give up all his Copernican ideas, which apparently he did, kneeling in front of the tribunal.
Despite his concession, Galileo quietly held fast to his beliefs throughout his final years under house arrest at his villa outside Florence.
Galileo is the first modern scientist in the sense that he actively engaged in observations with the telescope, he actively proposed theories consistent with the telescope, and he dared to challenge the orthodoxy of the moment.
Shortly before his death in 1642, Galileo inadvertently stumbled over a clue to Kepler's puzzle about the sun's strange influence on planetary motion. It was a clue that would help point future generations toward a theory of the Big Bang. Galileo's last published work dealt with the properties of falling bodies, which he noted always accelerated at the same rate, no matter what their mass. But it would take another genius to connect these two puzzle pieces together in a theory of gravity. Isaac Newton, born in 1643, explained the mechanism by which the planets moved. And not just how planets moved, but how everything moved, from planets to apples.
Newton was a towering intellect. It is astonishing what he did. His moment in the history of science is a sharp break in which the power of mathematics is really brought to bear on aspects of the physical universe. He is what set us down this path of using mathematics to describe the universe, showing that math, for some reason, is the language of the cosmos.
Kepler observed through his data the attractive effects of the sun. It acted like a giant magnet. Might the planets also be like magnets? Galileo had theorized about the rate of acceleration of falling bodies, and he realized that regardless of their mass, falling objects always fall at the same rate. But years later, Newton had something to add to Kepler and Galileo.
The great insight Newton had was to bring Galileo and Kepler together and to realize that the things that make projectiles move and fall on Earth is the same thing that makes the planets go around the sun in the skies.
In a sense, the planets are falling toward the sun, just as Galileo's falling bodies fell towards the Earth. The crux of it all is gravity, the strange action at a distance that holds everything together. Newton didn't just observe gravity, he drew it up as a provable equation, showing that gravity was the energy, the tether, that kept matter, objects like the Earth and the planets, from flying headlong into interstellar space. Gravity, the attractive force that affects all matter in the universe, gives the universe order, and gravity is described by the science of physics.
Newton created physics. He was the person who first saw the fundamental laws underneath all of these observations. Newton's laws explained almost everything.
Newton postulated the laws of motion, the universal rules of gravity. He begins a new era in science, using observations and mathematics to describe the laws of nature.
He could, in fact, show that the rate at which an apple was falling to the earth was directly related to the way the moon was falling around the earth, because he understood that the same laws that led to the motion of the planets around the sun led to the motion of the moon around the earth.
Newton's great book, the Principia, revealed that the tides, the velocity of orbiting planets, even the shape of the Earth could be explained through the pull of gravity, because everything with mass exerts a pulling force on everything else with mass. The moon pulls the oceans. The Earth pulls the moon. The sun pulls the Earth. And the closer these objects are to each other, the stronger gravity pulls. Newton's Principia is such an engulfing work of genius that it almost makes up for one disconcerting fact. Although Newton formulated the laws that govern gravity, he never explained or even understood why it works. And gravity, when you think about it, is bizarre.
Understanding how the Earth knew where the sun was to go around it. What happened if the sun suddenly moved? What would the Earth do? This action at a distance is something which he gave up on. He said, I'm just not going to worry about that question because the laws work.
Although physicists still struggle to define gravity, Newton had gone far in revealing it. 200 years later, Albert Einstein would rival Newton's genius, not only creating new laws of physics, but reinventing the universe. Albert Einstein, born in Germany in 1879, may be the most famous scientist who ever lived because of what he did here in Bern, Switzerland in 1905. Failing to secure a teaching position after his years as a student, Einstein took a job at this patent office. And then he began to think. In fact, he thought up a revolution in space and time. Without Einstein, we might still be struggling to understand how the universe really works.
I think if we were asked who was the greatest scientist of the 20th century, most of us would say Einstein. And I think it's partly because of the fact that there's a natural fascination with space and time, the mysteries thereof. But also I think it is partly because he fitted the archetype public perception of a scientist.
Einstein didn't mean to lead us to the origin of the universe. He didn't even like thinking about it. The idea of a beginning suggested a dynamic, finite universe. And Einstein preferred a static, infinite one.
Philosophically, he believed that the universe was eternal, and that a universe that had to have a beginning or an ending was unaesthetic, it was not pretty.
The idea that the universe was infinite and eternal was an old one, embraced by scientists like Einstein because it was easier to think of the universe as always existing, rather than as having been created. Created how? By what? Unfortunately for Einstein, his new understanding of forces like gravity would ultimately suggest the universe was not eternal. Einstein's ideas were so bizarre, it's almost easier to think of them as applying to some other crazy carnival world. But strange as it may seem, our world is Einstein's world.
gather round, don't push, don't shove, make sure you get a good view. The show is about to start, you don't want to miss a thing. Hurry, 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 ladies and gentlemen, step right up to Einstein World, where things are always what they appear to be, but not always what you'd expect. First up, the wondrous Einstein himself. Born missing a region of the brain that influences speech, he did not speak until the age of 3. However, his parietal lobe, responsible for mathematical thought and spatial relationships, grew larger, making his entire brain 15% wider. Notice the enlarged brain.
Einstein was the master of what we call the thought experiment. Thinking through an experiment that you can't literally carry out, but based upon your insights from thinking about it, sometimes resulting in a revolution in how we think about the universe.
In 1905, Einstein published his theory of special relativity, which explored the link between space and time.
In Einstein's view, there isn't really a separate thing. There's space and then there's time. But there's just one thing, space-time, that we all live in.
He thought of this new space-time as a fabric weaving together space and time. In 1915, Einstein developed his theory of general relativity, which modified special relativity to include gravity and its effects on this fabric of space-time.
Welcome to the bouncy trampoline of gravity. We've taken our fabric of space-time, stretched it taut, and placed a heavy weight on it. See how it warps the fabric of space-time. When we roll the ball across the fabric, it magically seems to be drawn or attracted to the massive weight at the center.
General theory of relativity was a new theory of gravity, one that told us that gravity worked because space and time were curved in the presence of matter and could respond dynamically. Space itself could expand and contract in the presence of matter. A crazy but true idea.
Mass is a term used to describe the energy and matter that objects contain. The larger the mass of an object, the greater its distortion of the space-time fabric, the stronger the effects of gravity.
Gravity is not really a force. It's a fabric. It's a shape of space and time. And we just move along the curves of these shapes. And the act of doing so takes what would otherwise be a straight line to you and bends it into what you now describe as orbits, as trajectories, as pathways through the cosmos.
Einstein said not even light can escape the effects of gravity. As crazy as this sounds, proof conveniently arrived in 1919 in the form of an astronomically large experiment based on a solar eclipse.
General relativity said that if you look at a star on a path of light that goes right past the sun, you would see it shift just a little bit because of the gravity of the sun. So Arthur Eddington actually went out to test that theory during the solar eclipse of 1919 and actually photographed stars when the sun was blocked by the moon and you could see the stars behind it.
The ability to see objects that were actually behind the sun proved that objects could warp space-time. Einstein became a superstar overnight. He received the Nobel Prize in Physics in 1921. But general relativity opened a Pandora's box for Einstein.
One of the consequences of Einstein's theory was that the universe must either be expanding or it must be contracting. But sitting still, being eternal, is not a valid solution. And that was a problem.
A problem because if you introduce mass into Einstein's static universe, all that mass will, through gravity, draw together. What was preventing this from happening?
When you put matter in a spherical universe, you know, matter attracts each other and the thing is unstable.
To keep gravity from collapsing the universe, Einstein postulated a force equal to and opposite gravity. This constant force perfectly countered gravity to achieve a static universe. Einstein searched for this cosmological constant, convinced it was hiding in his equations. But he was wrong.
If Einstein had had the courage of his convictions, in some sense, he would have recognized that the static universe he believed in was not compatible with the theory that he'd come up with.
In fact, relativity pointed to the idea that the universe wasn't static, but expanding.
Sit right down, folks, and enjoy the magic space-time projector. Watch the universe, linked by 4 dimensions, move forward in space-time.
Einstein himself didn't want to make that prediction that his own theory was sort of screaming to make. It was, I suppose, the one time in Einstein's career where his courage failed him and he didn't make the bold prediction that was actually staring him in the face.
Einstein's theory inevitably leads to the idea of a moment of creation.
Now brace yourself for the part that Einstein couldn't watch. Stand back, everyone, as we run the projector backwards.
Despite what Einstein believed, his theory pointed to a dynamic universe that was once much smaller.
The universe shrinks down to the size of an atom.
Einstein couldn't make that leap, but others would. A dynamic and expanding universe fit nicely into a theory called the Big Bang. At the dawn of the 20th century, Albert Einstein may have inadvertently led us to consider the scientific possibility that our universe began. But the idea of a beginning for everything has strong religious overtones.
A culture will ask itself, where did I come from? It's a very important question for humans. Because if we don't know where we came from, we don't know who we are.
For thousands of years, the origin of our world was a matter for religious scholars, not scientists.
There's a difference between science and religion. They are looking at the world in different ways. They're asking different questions. Science essentially asks how things happen, what's the process of the world. Religion is asking what I think is a deeper and more interesting question. Why are things happening? Is there something going on, some meaning and purpose in the world?
Religion and science have been uneasy companions, if only because they seem motivated by the same quest for truth. So it was ironic that an early champion of an objective scientific theory for the origin of the universe was an ordained Catholic priest. And what a strange twist that his science-based solution would appear so religious. That the universe didn't always exist, but that there was once an in the beginning. Father George Lemaitre argued that the universe was born.
Lemaitre is one of my ideals. For a few years, from the late 20s to the early 30s, he was the one who best understood the concept of an expanding universe and introduced many of the ideas we're still exploring.
Lemaitre studied Einstein's theories during the 1920s and proposed a radical idea, one that even the great Einstein would reject. He said the universe wasn't static, but was actually expanding.
Lemaitre studied Einstein's equations kind of without prejudice. And when he found that these equations suggested a universe that would be expanding today and therefore ever smaller in the past, he decided to take that solution seriously.
If the universe was expanding, Lemaitre reasoned, it was smaller yesterday than it is today. Therefore, it must have been ultimately unimaginably small. Lemaitre believed the universe began with what he dubbed a primeval atom, an infinitely dense, hot, cosmic egg that at some time in the past exploded, setting the universe into motion and leading to the formation of everything we know.
When Lemaitre told Einstein about this solution, Einstein reportedly said, "Your mathematics is correct, but your physics is abominable."
But this abomination soon received compelling corroboration in 1925. In the mountains above Los Angeles, astronomer Edwin Hubble saw something in his telescope that destroyed Einstein's cosmological constant and altered our image of the universe.
In the 1920s, we had this very comfortable picture of the universe. The universe is the Milky Way galaxy. You see this huge swath of milk that cuts across the night sky called the Milky Way, consisting of about 100 billion stars. It was about 100,000 light years across. That was the universe in the 1920s, very comfortable.
Hubble peered deeper into the universe than Galileo could have imagined, using the most sophisticated telescope of his day. He revealed our sun as one star among billions within the Milky Way galaxy. But was the Milky Way all there is? If so, exactly how big was it?
Since the advent of powerful telescopes, astronomers have been looking in the skies, but they had no good measure of how far away things were, except for very close stars. Edwin Hubble solved that problem by coming up with what's called a standard candle, a star of known brightness. And if you know how bright it is, you can measure how far away it is, because the dimmer something appears, the further away it is. Just like a train in the distance, the light seems dim and it gets brighter and brighter and brighter as it approaches you.
Hubble found one of these standard candles within a spiral swirl of stars called the Andromeda Nebula. People thought Andromeda was just a wisp of stardust inside the Milky Way.
Then Hubble calculated the distance, and then he realized that galaxy is 1,000,000 light years away. That was the eureka moment. And he had this epiphany. He realized that the Andromeda galaxy was an island universe, just like the Milky Way galaxy. So in one instant, the universe went from being a comfortable Milky Way galaxy 100,000 light years across to becoming this fantastic universe, perhaps billions of light years across. And it all happened in just one night.
This alone would have ensured Hubble's immortality. He single-handedly grew the universe from a quaint one-galaxy town to a potentially billion-galaxy metropolis. But Hubble went one further.
He also measured the behavior of those galaxies, and in 1929, he came to the conclusion that most galaxies are moving away from us. Not just there are lots of them, but they're actually moving away from the Milky Way, and in fact, they're moving away from each other.
In other words, the universe is expanding, getting bigger every second. And if you went back in time, the universe must have been smaller. Based on the speed of expansion that Hubble measured, he could calculate the age of the universe.
Hubble actually came up with an estimate for that using his data, and he said the universe is about 2 billion years old, right? That was bad because they already knew that the Earth was older than that.
Hubble was on the right track. His formula for determining the age of the universe was correct, but his measurements were inaccurate. And this discrepancy gave some scientists room to quibble with Lemaitre's theory. But other, less scientific reasons also may have contributed to Lemaitre's superatom being estranged from the physics community throughout the first half of the 20th century.
I think there was some resistance to having somebody in the scientific camp and in the religious camp, but did that make it difficult for some scientists to perhaps embrace him as much as they would someone who was not in that position? Probably.
Lemaitre's proposal may have left him estranged from his fellow scientists, but it appealed to Pope Pius XII, who interpreted the theory as a de facto proof of the biblical story of Genesis.
Lemaitre wrote to the Pope and said, stop saying that. This is a scientific theory that makes a prediction that you can measure, makes many predictions you can test. But your beliefs are independent of those predictions.
Lemaitre's theory could be measured, but proved? It seemed unlikely, billions of years after the fact, that the Big Bang's smoking gun would turn up. And unless this smoking gun was found, other theories of the universe could be proposed, and Lemaitre's cosmic egg would remain unhatched. By the middle of the 20th century, it seemed as if the primeval atom theory, with the universe expanding violently outward from an infinitely small speck, would never gain wide acceptance. Hubble's incorrect estimate for the age of the universe allowed a competing theory to emerge from the halls of Trinity College, Cambridge.
There was a tenable alternative to the Big Bang theory, namely the steady-state theory, which allowed the universe to exist from everlasting to everlasting.
The steady-state theory championed the static universe that the primeval atom concept rejected. Proposed by astronomer Fred Hoyle, it was built upon a theory of the origin of elements, nitrogen, carbon, and more than 100 others in the periodic table. Under extreme temperatures, hydrogen fuses to form helium, and helium fuses into entirely different, heavier elements. Fred Hoyle believed this nucleosynthesis, the creation of new elements, took place in the cores of very hot stars.
That was an absolutely staggering achievement at the time. Hoyle's achievement was to teach us that everything after helium in the periodic table is actually stardust. It is in the stars that these things were made.
But the theory couldn't account for the formation of hydrogen and most of the helium in the universe, because the first stars must have been made of hydrogen already in existence. This existing hydrogen makes up more than 74% of the detectable universe. Hoyle sidestepped this problem by adopting a widely held belief that hydrogen and helium had always existed. In fact, according to Hoyle, the entire universe had always existed. No beginning and no end, just a steady state.
In a nutshell, a steady-state universe is a universe that's always been here, always looks like it does now, always has the same average density, has the same temperature,
There was just a little problem though, which was people knew the universe was already expanding. When a distribution of matter expands, it becomes more dilute. Now, if the universe is very old, it would be infinitely dilute.
Hoyle fixed this flaw by assuming that somewhere matter was always being created in the universe. But the wholesale creation of matter was a hard pill for physicists to swallow. And Hoyle had a nemesis of sorts in the Russian physicist George Gamow, an admirer of Lemaitre's primeval atom.
Gamow was usually present in these discussions, and he always brought up nasty questions for Hoyle to consider. Questions that the steady state had difficulty dealing with.
Gamow turned to atoms, as Hoyle did, to support his competing theory. Gamow suggested that hydrogen and helium and the other elements were created in the first fiery minutes of the universe, in a Big Bang, when temperatures were thousands of degrees hotter than they are in the core of any star. But Gamow was a better idea man than he was a mathematician.
And he had to turn to this phenomenally talented graduate student of his, Ralph Alpher, and it was really Alpher who was able to push this idea through and come to a conclusion that if indeed the universe synthesized the early elements, there should be roughly 10 times as much hydrogen as helium. And that matched the observations. Fantastic moment.
Alpher, with colleague Robert Herman, refined Lemaitre's prediction of detectable remnant heat from creation, a strong clue supporting the Big Bang.
George Gamow and his students asked a very simple question. If the Big Bang was so hot then the aftershock, the afterglow, the echo of the Big Bang can't be so cool now. So the residue should be measurable today.
Unfortunately, no one had the right telescopes in 1949 to measure the radiation, or heat, left over from the moment of creation. And at the time, there were other problems with the Big Bang theory. It offered no explanation as to the origin of the elements beyond hydrogen and helium. At the same time, steady state garnered widespread media coverage.
The steady state theory was popular with the general public because Fred Hoyle was a master of popularization and just going out and marketing his wacky idea.
Ironically, the term Big Bang was coined by Hoyle in 1949 during one of his popular radio broadcasts. He later used it as a term of derision.
I think there was a dislike in their relationship. They didn't see eye to eye on most of the things they were thinking about. So I think Hoyle came off the worst in battles. I think he did more fighting for his views than was merited, but that's a personal opinion.
Fred was a very, very brilliant and innovative sort of person. Ideas just poured out of him. Some of them were good and some of them were bad, and he didn't always know which was which.
By the 1960s, Hubble's inaccurate estimate for the age of the universe had been corrected to reflect more accurate data, resolving one challenge to the Big Bang theory. Still, it seemed the battle between the steady state and the Big Bang would end in a draw. But then, all of a sudden, scientists found a smoking gun, one nearly as old as the universe itself. Its discovery doomed one of these theories to the dustbin of history. For 500 years, science has been on a quest to discover where we belong. Now, astronomers struggle to solve the riddle of how it all began. Little did they know, the cosmos was whispering an answer back We just couldn't hear it. That whisper took the form of leftover heat generated when the universe exploded into being. The radiation that George Lemaitre predicted was out there, but that he had no tools to hear. By 1965, scientists had those tools.
The residue, the echo, the aftershocks of the Big Bang should be measurable today. But it took about 2 decades before our instruments became powerful enough to clinch George Gamow and his students' theory of this background radiation. The story of this radiation is like the Keystone Cops. First, we had George Gamow and his student. They had the theory, they had the numbers, but they didn't have the experimental apparatus. Then we had the group at Princeton. Well, they knew the work of George Gamow, but they had a very primitive instrument, not sensitive enough.
The group at Princeton included physicist Robert Dicke and some colleagues who supported Lemaitre's theory and wanted to look for some solid proof.
My teacher, Bob Dicke, he had the idea of looking for this radiation that would be left over from a hot Big Bang. He had 2 bright young people working with him, Dave Wilkinson and Peter Roll. He persuaded them to build a Dicke radiometer to look for this radiation. It was a shot in the dark. So his 2 young colleagues built one, pointed it into the air, and started looking when news of their experiment reached Bob Wilson and Arno Penzias.
Penzias and Wilson were 2 scientists working not on the Big Bang theory, but on satellite communications for Bell Labs in Holmdel, New Jersey. They were using Bell's huge radio telescope, only they couldn't get a clean reading. Instead, they got static noise.
The nature of this stuff is that it's random noise. And that noise is very much like what you would hear if you tune a TV set or an FM receiver to an unused channel. We didn't see what we expected. The antenna was actually getting more radiation than it should have. Our clear response to that was, there must be something wrong here, that we're getting all this extra noise.
What was this strange noise, and where was it coming from? Errant interference from nearby New York City? Airplane signals? Pigeon droppings inside the horn of the telescope?
We didn't doubt physics. Whatever it was had to be coming from somewhere, but we were really running out of ideas of where it might be.
In fact, this mysterious radiation was coming from everywhere, every direction and every corner of space. To Penzias and Wilson, that was just crazy. But Penzias and Wilson had unknowingly found what Dicke and his colleagues were seeking. What Gamow, Alpher, and Lemaitre had predicted. They'd found the smoking gun that proved the universe wasn't eternal.
The source was the creation of the universe, the Big Bang.
Penzias and Wilson and the Princeton team published their findings in separate papers in Astrophysical Journal in 1965. Their research crushed Hoyle's steady-state theory overnight. Finally, the Big Bang fit into the puzzle of the universe.
Our modern theory of the Big Bang is a remarkable achievement in that it allows us to make a model of what the universe was like right back to when everything was only a tiny fraction of a second old and was squeezed to immense densities and temperatures. And from that very early dense state, we can understand in broad outline how the universe expanded and cooled, how at some stage the first atoms formed, how at some later stage the first structures formed that made early stars, galaxies, and eventually planets and people.
In a hospital in Belgium in 1966, the dying Georges Lemaitre rejoiced at the news. He was not alone. Gamow and his team also felt justified.
We had been arguing for a different view of the universe, and lo and behold, that different view seemed to be the correct one. So that's always a vindication.
For their part in the discovery, Penzias and Wilson won the Nobel Prize in 1978. Though Hoyle's steady-state theory has fallen out of favor, his theory of nucleosynthesis was not rejected. While most scientists agree that hydrogen and most of the helium were created in the first few moments of the Big Bang, as Gamow believed, all other heavier elements, like nitrogen and carbon, were created later, in the hot centers of stars and in supernova explosions, as Hoyle suggested. So in essence, both Gamow and Hoyle were correct. Despite this partial vindication of nucleosynthesis, Hoyle, who died in 2001, never accepted the Big Bang.
He could not understand why people were so enthusiastic about a universe which had a finite beginning in what I suppose he thought was the recent past, a few billion years. He just never accepted it.
But the rest of the physics community, with almost total unanimity, did accept it.
The fact that we've discovered it has a beginning allows you to now ask a whole set of questions about how it began. And that's kind of interesting, that's kind of cool, because you can say, when did it begin? How was it different then than today? What changes unfolded between then and now to create the universe we now know?
But accepting the Big Bang theory and thinking it flawless are two different things. There were problems with the details of the theory, expanding problems. During the latter days of the 20th century, scientists examined problems with the Big Bang, even though the theory was generally accepted. One of the biggest problems was that the temperature in outer space was strangely uniform. Physicists didn't expect that the universe would have the same temperature roughly everywhere they looked. The universe is simply too large for one end of it to be the same temperature as another. Yet it is.
It's the same thing that happens if you have a bathtub full of cold water and you pour in some hot water in one extreme. It's going to be a while before the whole bathtub has tepid water, because it takes time for that hot molecules to propagate across and normalize the whole distribution.
The universe doesn't appear to be old enough for its temperature to have equalized yet.
The Big Bang could not explain why such faraway points have the same temperature. In the early 80s, Alan Guth came up with this idea that perhaps the universe came from a very tiny volume, so tiny that within that volume, early on, there was time enough for these different points to communicate and normalize that temperature.
Right after this moment, Guth theorized that the universe expanded even faster than light. Faster than the cosmic speed limit, the ultimate speed, according to Einstein.
What inflation refers to is a theory of what propelled the expansion of the Big Bang.
Guth called his theory inflation. In the earliest moments of creation, for instance, scientists believe the four forces of nature, including gravity and electromagnetism, were actually combined into a single superforce. During the Big Bang, this superforce split into the four known forces. But before it split, when the universe was incredibly small, Einstein's laws of physics, including the one that says nothing moves faster than light, didn't apply yet. Maybe at that moment, something happened that caused the universe to expand even faster than light. So fast that it locked in the uniformity it had when the universe was still small.
We don't know exactly when inflation happened. Most likely it happened when gravity had split off from the other three forces, but at a time when the other three forces were still very likely unified.
This hyper-expansion, if it happened, would lock in a certain uniformity of temperature. On June 3, 2001, NASA launched a satellite that could potentially determine one way or the other the truth about Guth's inflation theory. The Wilkinson Microwave Anisotropy Probe, or WMAP mission, planned to photograph the fossil remnant heat of the Big Bang that Penzias and Wilson had found. In other words, NASA wanted to take a baby picture of the universe that they could then compare with how the universe looks today. In February 2003, scientists got their first glimpse of WMAP's picture of the baby universe when it was a mere 380,000 years old. The clarity of the data stunned scientists.
The reaction people had when they saw this was, wow! It really was the way people had been speculating earlier on. Inflation probably happened.
To the untrained eye, the WMAP image looks like a speckled robin's egg. But to scientists, this was a stellar Rosetta Stone. These patterns represent the seeds that later grew into the vast expanses of stars and galaxies of today. Besides strongly supporting Guth's inflation theory, the data also gave us concrete clues to the age, composition, shape, and evolution of the universe.
Up until a few years ago, cosmology was quite distinct from other sciences, simply because there were more theories running around than data. And it was not until these satellites measured what was going on shortly after the Big Bang with such high precision that you could discriminate one cosmological model from another. And you could produce numerical results about the size of the universe, the age of the universe, the expansion rate of the universe, the contents of the universe. You couldn't do that before these data became available. Before then, it was this mixture of mythology and clever thinking.
Thanks to modern tools such as the WMAP satellite, physicists now have a model for the events just after the Big Bang. Less than a billionth of a second after the Big Bang, a bubble much smaller than a fraction of an atom forms. This is the universe. It is unimaginably small and unimaginably hot. Within this bubble, the four known forces of nature, gravity, electromagnetism, plus the strong and the weak nuclear forces, are a combined superforce. Gravity suddenly splits off from the superforce as the universe expands. As the universe expands, it cools, which somehow sets off a burst of energy, fueling the hyperinflation of the universe, suggested by Alan Guth. This inflation locks in the uniformity of the universe pictured by the WMAP satellite. The universe is still less than a second old when the superforce decays into the separate forces of nature. Roughly 3 minutes after the Big Bang, the temperature of the universe has dropped to a mere 1 billion degrees Fahrenheit, cool enough for atomic nuclei to form. The element hydrogen forms. Some hydrogen atoms fuse to create helium, as proposed by Gamow and Alpher. 380,000 years later, and light travels through the darkness. The burst of radiation that Penzias and Wilson found happens now. 1 billion years after the Big Bang, stars take shape, producing the heavier elements like nitrogen, oxygen, and carbon, as Hoyle predicted. Roughly 9 billion years out, matter and gravity combine to form a perfectly typical star. Pressure creates heat at its core. This heat triggers thermonuclear fusion. A star is born. Stellar outflow clears away residual gases. A circumstellar disk of dust remains that eventually accrete into an entourage of planets and moons. One of these lumps of stardust, after being pummeled for eons by residual solar debris, has temperatures warm enough to allow water to build up in the atmosphere. Liquid water gathers on the planet's surface. Underwater, mysterious chemical reactions ultimately form life. 13.7 billion years after the Big Bang, our universe is now 156 billion light years across. The sky is full of stars. Our solar system has 8 planets, more or less. The third planet is nearly covered in carbon-based life forms. Some are just realizing what infinitely small specks they are in the grand scheme of things. If you don't understand this process, that's okay. It's the culmination of millions of human brains struggling for thousands of years to figure out how the universe began and where man fits within it. It's enough to overwhelm any one human brain.
If I take seriously the idea that my brain was evolved to be able to throw rocks and pick bananas and stuff, it's pretty remarkable that we humans would be able to figure out much about physics, figure out much about things that didn't have survival value to our ancestors. Yeah, I think it's quite stunning how well we humans have been able to make progress in this regard and not go completely bananas in the process.
This is our story of everything, our world, our solar system, our universe, and how it all began. This is what we think we know. It's a work in progress. The script is still being written, but let's see how it ends. New York City. A beautiful but unremarkable autumn day, like thousands before it, and thousands to come, until there aren't any more autumn days. Imagine for a moment traveling into the future for billions of years. Past the end of human civilization and the lives of all living creatures on Earth. Imagine we are 5 billion years into the future. The sun is running out of the nuclear fuel that gives it fire. As it cools, it expands and reddens, coming closer and closer to Earth. It swallows up Mercury and Venus. Water on Earth evaporates, and Earth becomes molten again. When the fuel is gone, the sun's core ultimately contracts as it transforms from a red giant to a white dwarf. The expanding outer layers of the sun, called a planetary nebula, drift into space as ghostly shrouds of glowing gas. The planets that survive this process, the outer ones like Saturn and Neptune, are utterly changed by it. The planetary nebula blows away their gassy atmospheres, leaving small, rocky and metallic cores behind. The distant planets, no longer held by the less massive sun's gravity, drift into the vastness of space. Travel billions of years after that, and all remaining heat from the sun has radiated out, and its small, dark surface is the same frigid temperature as the rest of space. The sun is now a black dwarf. Now, billions of years later, propelled by a mysterious and only recently discovered dark energy, the universe expands ever faster, flying apart everywhere. On a grand scale and at a molecular one, expansion overwhelms gravity. Everything rips apart. Not just galaxies, solar systems, and stars, but even atoms. Finally, matter itself is torn asunder. This is the Big Rip, the big rest in peace for our universe, the legacy of dark energy, that stuff we still haven't figured out.
Right now, dark energy is mostly a code word for our ignorance of what this substance is. Some people think it's some sort of stuff. Some people think it's a constant that should be in Einstein's equation. Some people think it's just a reflection of the fact that we might have gotten our gravity wrong again.
Right now, the Big Rip theory of the end of the universe leads the pack. But who can say if this will remain our theory, or if some new discovery will challenge it? The stuff we haven't figured out yet, it goes on forever. One more blow to our centrality in the grand scheme of things. But that doesn't mean we don't know anything. Copernicus, Newton, Einstein, even Alpha, Wilson, and Guth. They've given us pieces of an endless puzzle. They've helped tell us how we fit in the picture.
Recognize that the very molecules that make up your body, the atoms that construct the molecules, are traceable to the crucibles that were once the centers of high-mass stars, that exploded their chemically enriched guts into the galaxy, enriching pristine gas clouds with the chemistry of life, so that we're all connected to each other biologically, to the Earth chemically, and to the rest of the universe atomically. That's kind of cool. That makes me smile. And I actually feel quite large at the end of that. It's not that we are better than the universe, we're part of the universe. We're in the universe, and the universe is in us.
We're not the center of the universe, but we are in it and of it, trying to figure it all out. There's so much we know, and yet so much we still don't know. We hold on tight as our little planet goes hurtling through space, around the sun, around the galaxy, around the universe. Don't forget to look up. There's so much to see, so much to know. Where do we begin?